A mass on a spring is a prototypical example of simple harmonic motion. And the reason it's simple harmonic is because a spring in what we call its linear regime obeys Hooke's law, meaning its restoring force is linear. So what that means is if I stretch a spring a small amount from its equilibrium position, the force exerted by the spring is proportional to how much it is being stretched. And the stiffness of the spring is characterized by what we call the spring constant. So let's imagine that I have a spring that is vertically mounted. And this spring, I'm going to say, is massless. Now this is an idealization, but really what we're saying is its mass is very small compared to other relevant masses in the problem. And here the other relevant masses in the problem are simply going to be a mass that I connect to the spring. So let's say I'm going to sketch this spring again, but now I connect a mass to it. And when I do so, it stretches. Okay, and the larger the mass I hang to the spring, the farther and farther it stretches. And what determines the stretchiness of the spring is something we call the spring constant. The spring constant K is a measure of the stiffness of the spring, or the amount of force it takes to stretch the spring per unit meter. So I'm going to call this the stiffness of the spring, call it K. So the force exerted by the spring, F spring, is equal to negative K delta X, where delta X is simply the amount, or the distance, I should say, that the spring stretches when I add a mass to it. Delta X, the displacement. All right, now the goal here is, what we want to accomplish here is we want to find a way to determine this spring constant K. And I'm going to explain two different methods to determine the spring constant. That's our goal. Determine K. And there's two methods that I'm going to look at. The first method, number one, is a static determination. Okay, now on the static determination, basically what we can say is we can set up a Newton's second law type of equation and say that I'm going to draw a free body diagram for the hanging mass. And a free body diagram for the hanging mass, we will notice that there's only two forces that are acting on it. If I isolate the hanging mass, I have the force of the spring upwards and the gravitational force pulling downwards. And those two forces equal one another, which is why the mass doesn't move at all. All right, now let's consider that this vertical direction, I'll call my y direction, being upwards. So I can write Newton's second law, and Newton's second law says if I sum up all the forces in the y direction, this equals mass times the acceleration in the y direction. And since we're in a static situation, or in a situation of equilibrium, this means that the acceleration equals 0. So there's 0 acceleration, which means that the force of the spring, which is my positive force, in the positive y direction. Force of spring minus force of gravity equals 0. Or in other words, slightly rearranging this equation, I can write force of spring equals F sub g, adding force of gravity to both sides. Now the spring force, the magnitude of that force is just equal to kx, or k delta x. And the force of gravity, which is the weight of the hanging mass, is simply m times g. So if I solve for delta x, I get m over k times g. Or another way I might write this is I might just switch around the m and the g, and I might write delta x equals g over k times m. Okay, so this is simply, this expression right here simply comes from Newton's second law. Now, how are we going to use this to statically determine the spring constant? Well, in this equation right here, there are basically two variables which we can very easily measure. We can measure our m. And the m I will call the independent variable. And the delta x is the dependent variable. And what this means is simply that I can add experimentally however much mass I want to the spring, and then the system mechanically responds by giving me a certain delta x expansion. So if I collect a series of data points, if I take some data, the data I can take is, for various m's, I measure the resulting delta x. And I get a number of different points that correspond here. Now what I'm going to do is I'm going to take that data and I'm going to plot it. I'm going to make a graph here. And I'm going to plot on the vertical axis, I'm going to plot delta x. On the horizontal axis, I'm going to plot m. And then I'm going to start to plot all my data points. And what this equation says is that we should get a linear line if I do a line of best fit. In Excel or some other graphing software, and I use a linear regression method, the line of best fit will then pop out a slope for me. And if I just stare at this equation right here, we know that the equation of a straight line is equal to y equals mx plus b. And if I compare that with simply the equation that I'm plotting right here, which is delta x equals g over k times m, what we see is that my y is my delta x, my m is my x-axis, and whatever multiplies the x is my slope. So the g over k, the slope, is equal to g over k. So what the way that we find the spring constant here is by using the linear regression to find the slope. We take the acceleration due to gravity to be 9.8 meters per second squared, and that gives me a value for k. So we're going to take here g equal 9.8 meters per second squared. All right, now this is method number one. This is the static determination of the spring constant. Now we're going to look at a second method here to determine the spring constant, and that's what I call the dynamic determination. So number two, is the dynamic determination. And for this scenario right here, I'm going to start out with the same picture of a mass on a spring. Right, and in this case, I'm just going to fix the mass. For this case, M is fixed. So what I'm going to do is, given that it stretches a certain distance, I'm going to call this distance right here, I'm going to call this y equals 0. This is really my equilibrium, my line of equilibrium. This is where the system tends to settle around. Now imagine I take this system and I stretch it such that I pull the mass below its equilibrium position. And I pull it below its equilibrium position some distance. I'll call y equals, if I take upward direction, y to be positive, I'll say this is y equals negative a. Now if I release the block from this location right here, you can imagine what will happen. It will begin to basically oscillate back and forth about its equilibrium location. So half a period later, the block will have reached this location up here. Right, and strictly speaking, it's not going to get any higher than y equals a. And we can see that just from the fact related to energy conservation. Once the block is all the way down in its lowest position, it has potential energy that's stored in the stretching of the spring. So the amount of energy stored in the spring could say at the bottom energy E is equal to potential energy plus kinetic, and the potential energy due to the spring is 1/2 k, in this case y squared. So when you're at the bottom here, we have U max, maximum potential energy, but no kinetic. And in the center, we have U equals 0, but we have maximum kinetic energy. And then that kinetic energy is again transformed into potential energy as the block moves upwards. And kinetic energy equals 0 up here. Now, so far, I've only indicated potential energy due to the spring, but there's also potential energy due to the gravitational field, and that would be 1/2, or sorry, that would be mgy. All right, now, how are we going to use the dynamic determination to actually determine the spring constant in this case? Well, I'm going to do a free body diagram again for the hanging mass. Okay, so I got to isolate the mass and draw all the forces that are acting on it. And you can see on the right, I'm going to skip a couple steps here and just do the following. Is first of all, I know that when I'm in my equilibrium position, right here, the spring force balances the force of gravity. Those two forces balance each other out. However, when I pull it a little bit beyond its equilibrium position, now the spring force is a little bit larger in the upward direction. So if I was to draw a free body diagram for the mass, I'd have a spring force up, and it's imbalanced by the force of gravity, or the force of gravity is not quite as large as a spring force. That's why it tends to move back towards its equilibrium position. Now what's going to happen here is the following is, let's just write out Newton's second law. So Newton's second law says sum of the forces in the y direction equals m times a sub y. And summing up all the forces in the y direction, what I'm going to have here is simply the following, is negative k y equals m times d2y dt squared, or the second derivative of y with respect to time. Now if I take this equation and I rearrange it slightly, so I'm going to write d2y dt squared equals negative k over m times y. This is a second order linear differential equation. When I take the derivative I get of some unknown function y, I simply get that function back with a minus sign and this constant factor multiplied out front. So the easiest way to solve this equation is simply using a guess and check. And since this is one that appears very often in physics, and the solution is simply a sinusoidal function, and since it's the second derivative, there's going to be two integration constants, or basically two constants which characterize the initial condition. So I can write my solution as follows. Y as a function of time is equal to some y max cosine omega t plus phi naught. My two initial conditions are going to be y max and phi naught. That's what the experimenter determines. The experimenter determines basically where the block starts, which is the y, and then the phi naught with which phase it starts. Now just going back here one moment here, you might wonder, why do I only have minus k times y as my force? Isn't there also a, just as there was in this case, a k delta x and an mg acting in opposite directions? Well, of course there is, but they cancel each other out. That's what this shows right here. They're acting in opposite directions, they cancel each other out, and the equation just simplifies to this, and I just simply get the equation for a simple harmonic oscillator where omega is equal to the square root of k over m, and omega is also equal to 2 pi over t. And angular frequency is telling us something interesting about how long it takes for the oscillator to complete a complete cycle, that is to go all the way up and to go all the way down. So let's rearrange this equation slightly to solve for t, because t is something we can measure very easily experimentally. So I can write t as, I'm going to multiply both sides through by t. So t is equal to 2 pi square root m over k. Now this equation is still a little bit clumsy, so what I'm going to do is I'm going to square it to get rid of the square roots. And what I get is t squared equals 4 pi squared over k multiplied by m. Now this equation right here is going to give us another way to actually measure the spring constant, K, because it relates the period and the mass. So again, the mass is my independent variable, and the T is dependent. Meaning it's set by the physics of the problem. I don't get to determine the period, all I do is measure it. So again, if I take some data, and the data I'm going to take is mass versus period. I'm going to now vary the mass and look at how the period changes as I vary the mass. I'm going to want to also, in my data table, create another column, which is t squared. And now what I'm going to do is I'm going to create a graph of t squared versus m. And according to this equation, what I should get is, if I take all my data, t squared is proportional to m, and the proportionality constant is 4 pi squared over k. So once I plot this graph, what I get is a straight line. And if I compare this to that of an equation of a straight line, y equals mx plus b, the y-intercept is 0, x is m, y is t squared, and m is 4 pi squared over k. So the slope is equal to 4 pi squared over k. So once I do my linear regression or my line of best fit using Excel or another plotting software, I basically just solve for k, and I have a dynamic determination of k simply by watching the mass oscillate back and forth as it goes up and down here. Now, a couple points just to notice here is when I look at the k I get from the dynamic and the k I get from the static, they should be very close because it's the same spring. And we're assuming we're not overstretching the spring, that you've taken it out of its linear regime, but it's still obeying Hooke's law, or it's still a Hookean spring. And the other thing we want to just consider here is the following is, now that we have actually compared the two springs, we've got the two spring constants, we can ask ourselves the question, what would happen if the spring itself had mass? Well, if the spring itself had mass, would it still be simple harmonic motion? That's something you're going to consider in this particular experiment.